Swayam Prabha. Digital India. Educated India.
take the pth power, then you integrate over all time, and then you take the pth root. Okay, that's the idea. Take the vector norm to the pth power, integrate it for all time, and then take the pth root. This is what is the p signal norm. All right. Further, if you look at the infinity norm, as you notice, the infinity norm is always different, slightly different as compared to the rest of the norms. Right? So the infinity norm is simply the supremum over all time of the vector norm of the signal. Okay, so as you see, in the first definition, we integrate over time, and in the second one, you take supremum over time. Therefore, the time argument completely vanishes on the left-hand side. And this is what I've said, that the signal norms tell you something about the behavior of a signal for all time. Yeah, it's like a global property of a signal, if you may. I mean, global in time property of a signal. Okay. Now, the important thing to notice is that the vector norm here is arbitrary. Yeah, if you remember, for the matrix norm, I had mentioned very clearly that if you want the p-induced matrix norm, you take the pth, you take the p vector norm here on the right hand side. But now there is no such thing. All right, that is, this p is coming from this p and this p. All right, this p has no connection to which vector norm you use. Right? So you're free to use any vector norm. The only requirement is that for one problem, one complete problem, you should not use different vector norm notions. You should use the same vector norm for every norm computation in a particular problem. Otherwise, there will be inconsistencies in your result. Yeah, that's it. That's all you need to remember. Otherwise, this is an arbitrary choice. Okay. Now, as we mentioned already, this norm xt signifies any vector norm, and the choice doesn't matter. However, do not switch in between. That is, in between a problem, please do not switch between the vector norms. Okay. So one of the important things about these signal norms is that they actually define spaces of signals. In fact, they define vector spaces of signals. And this is a very, very key, very, very critical notion. Yeah. So what do we say? We say that if xp is finite, then for any p, that is 1 to infinity, then x is said to be in LP space. So LP is a vector space of signals. Okay. One of the critical things to notice is that until now, when we talked about Rn and Rp and Rk and so on, we're talking about a finite dimensional vector space. But here, each LP, for example, L1 space, L2 space, etc., is an infinite dimensional vector space, because these are spaces of functions. Okay, so if you've seen a serious course in mathematical analysis and vector algebra and vector spaces, you will know these notions. If not, you can read upon them. But the idea is that each LP space, that is L1, L2, L3, and so on and so forth, L infinity, each one of them is an infinite dimensional vector space. Yeah, but they are vector spaces nonetheless. Okay. And how do you categorize them? You say that if a function has a finite LP norm, then it belongs to LP space. Yeah. And these are very, very useful regularity conditions which appear in a lot of places in mathematics, like approximation theory, Fourier transforms, and so on and so forth. Yeah, so it's not just significant here in the context of controls and adaptation, but in a much more general setting in mathematics, these are rather critical spaces. Okay. So anyway, I mean, so we also have a discrete counterpart for this, which is the small LP space. What will happen? For the discrete counterpart in these definitions, the integral gets replaced by the summation. That's it. Okay. And then you have a small LP space instead of the cap LP like we have now. But in this course, of course, we are concerned only with the capital LP space or LP space. Yeah. Another thing to notice is that a signal in L infinity is the same as the signal being a bounded signal. Okay, so this is another important categorization to remember. Okay, it's not very difficult to prove. You know that this is what is the infinity norm of a signal, right? You know this is the infinity norm of a signal, right? So suppose I assume that uh, xt bounded. What does it imply for a signal to be bounded? Implies there exists a positive number such that norm of xt less than equal to m for all t greater than equal to 0. This is what it means for a signal to be bounded. Okay, so if the signal is bounded, what happens to x infinity? What can I say? Let's see. I can say that, notice that this quantity is less than equal to m for all time. So what does this imply? This implies, so this particular piece of information tells me that soup for all time of xt is also less than equal to m. Alright, and this immediately means that x is in L infinity, right? Because the infinity norm is bounded, right? Great, great. So I hope that much is clear to you. Okay. So now, what about the other way around? If the infinity norm is bounded, so say I know that if x infinity is equal to m, what do I know? I know that soup of norm xt is equal to m, right? Which implies, and this immediately implies that norm xt less than equal to m for all t greater than equal to 0. Why? Why? Because soup is just a upper bound. It's the least upper bound, but it's still an upper bound, right? Therefore, if you say that soup xt is equal to m, then at each instant in time, that is each norm xt has to be less than equal to m. There is no choice. Okay, so done. And this is of course the definition of a bound, right? Of a bounded function. Also, they're equivalent. These are equivalent notions. So as far as notation is concerned, the signal norm never has a time argument, like you saw, because the time argument gets neutralized by either integration or by taking supremum. While the vector norm always has the time argument, so please be very very careful even in the writing process. The signal norm never has the time argument, but the vector norm has to be evaluated at an instant in time. Otherwise, there is no question of a vector norm. It's not a vector at all if there is no time. Right? So we have to choose a particular time, say 1 second. We have to insert that in x, and then you get a vector, a fixed vector, and then you can compute a norm just the way we have learned how to. All right. Great. So one of the cool things that we know about vector norms is not something we'll prove, is the notion of norm equivalence. Okay, what is that? It says that you can take any two vector norms, say p norm and a q norm. All right, you can take any two vector norms and they are relatable by constants alpha and beta. That is, the q norm is lower bounded by alpha times the p norm and upper bounded by beta times the p norm. Okay, so this is always true for any vector norm. However, one of the interesting things to note is that this is not possible in signal norms. Yeah, and it's very easily shown by a very simple counter example. Suppose I take x of t as the vector signal cosine t and sine t. All right, so this is a counter example of why such equivalence is not possible. Right, now let's look at the infinity norm. Right, so I will compute x infinity, and what is this? This is soup t greater than equal to 0 norm xt, and I choose to use the 2 norm, right? Because it's easy to compute. So what is the 2 norm? So this is soup t greater than equal to 0 cosine squared t plus sine squared t, right? and that's just equal to 1, because this quantity is 1, so supremum of 1 over all time is just 1. Okay, so this is, so what have we shown? That the infinity norm is 1. So I can even say that x belongs to L infinity as per our definition. Now let's try to compute, say, 1 norm. Okay, so what is x1? It is now integral 0 to infinity norm of xt, and I take the two vector norm here again, dt. Okay, what do I get here? I get, again, this is just equal to 1, so I get infinity here, and because the integrand is 1 integrated from 0 to infinity, so I get infinity. So what have I just seen? That x does not belong to L1. In fact, you can show that x does not belong to, you can show that x does not belong to any LP, right? So what do we know? We know that x belongs to L infinity. So x belongs to L infinity, not to any other LP, right? So therefore all the other signal norms become infinite, right? And therefore there is no such possibility of norm equivalence. All right, so it may just happen that it's a infinity norm is bounded but the other norms are unbounded and so on. So therefore there's no question of having inequalities like these, because this by definition means that all the vector norms have to be bounded, all the norms are bounded. Now in the signal norm case, one cannot even guarantee that all norms are bounded. A signal which is L infinity may not be L1, a signal which is L1 may not be L2, and so on and so forth. All right, so this is a rather critical thing to remember. There is no norm equivalence. Okay, great. So what have we sort of seen today? We have sort of completed the proof of the Cauchy-Schwarz inequality for a more general case, more general vector spaces, more general inner product space, if you may. After that, we started to look at the notion of signal norms, which is the next level of notion that we need to complete different proofs that will occur through through this course. In the process, we also learned about the notion of LP spaces, right? And finally, we also saw that there is no norm equivalence in LP spaces, unlike the vector norms, where norm equivalence is a pretty standard notion. Right? Great. So this is where we will conclude today. See you again next time. Thank you.